Hello everybody. Today we're going to look at topics in Chapter 4. It covers amplitude modulator and demodulator circuits. Now there's a lot of information in this presentation, and not all of it is are things that I'm going to be emphasizing in the class. Keep that in mind as we're going through this. Some of the things I will be being fairly brief on, because there's, like I say, in these slides, there's a lot of information. There is particular topics in this presentation, however, that are very, very important, and I will focus on those. But some of the details in the circuitry and so on, I would like you to be able to recognize them, but not necessarily. Will not have to draw them or reproduce them in any way. But I'll get more into that as we go along here. So again, amplitude modulator and demodulator circuits. Last week we looked at the principles of amplitude modulation. Now we're going to see actually how we do it with hardware and how we demodulate it. Okay. So my slide's working here. So we're going to again, do a quick review of the amplitude modulation principles, just one or two slides on that. We're going to look at amplitude modulators and then amplitude demodulators. And then the last two topics, balanced modulators and SSB circuits. Not going to focus on those that much, a little bit, but again, it gets pretty high level. It can get fairly high level there, and we don't really need to do that at this point in time. But there's a few topics in there that are important that I'll focus on. So once again, this is the basic equation for the AM signal. So we have the carrier sine wave here, we have the modulation sine wave here, and this is another product of the carrier sine wave. And remember, when we multiply all this together, what do we get? We get three sine waves using the sine X, sine Y, or sine A, sine B trigonometric identity which we presented earlier, which gives you the upper sideband and lower sideband sine waves. You end up with three sine waves from this equation here. So they're really all sine waves. The A is the gain of the carrier sine wave, basically. So basically what we're doing is we're amplifying the carrier sine wave using the modulation signal, modulation sine wave, if you will. Obviously, the modulation is not always a sine wave, right? If it's somebody speaking like me right now, that's hopefully not a sine wave, otherwise it'd be very boring. But for instructional purposes, we always just use a sine wave. Makes things certainly easier to write on a whiteboard, for example. So here's a little block diagram. This is nice. You might see this again, hint, hint, on the midterm. But you have a modulating signal. We have a multiplier that multiplies the modulating signal with the carrier. That also gets summed with the product of that. The carrier gets summed with the product of that and results in the AM waveform. So it's a block diagram of the equation we just looked at. How do you make AM using parts, using hardware? Well, a lot of times we'll use a diode, okay? You have to multiply signals together, right, in order to create the AM waveform. And one way to do it is to use balanced modulators and diodes to do that, because diodes have this square law function. And it allows you to basically very quickly and simply multiply two signals together. Bipolar transistors and field effect transistors can also be used to give a square law response, okay? And we'll look at some schematics here in a moment. Now, when we do that, what happens is you get not only the product of the two sine waves, if you will, you get a bunch of other products, which are called intermodulation products, which are harmonics of what you want, Okay, what do you want? You want the carrier and you want the two sidebands, right? That's the goal of creating an AM waveform. And you can use a diode to do a square law function to do this, except it creates all this other stuff. Well, how do you fix that? Well, you can just use a bandpass filter and only allow the carrier and the sidebands out the antenna. All these other intermodulation products, they get filtered out. And yeah, here's a little diagram, the output spectrum. Here's your output AM wave, carrier, lower sideband, upper sideband, and here's all this junk, upper harmonics and these lower harmonics. We even have the modulation frequency in here. We don't want any of that on our AM wave, right? That's what happens right here at this load, right? So we have the carrier and the modulating signal summed together. They're in series, kind of like a couple of D batteries in a flashlight, essentially. Goes through the diode, creates your AM wave. Terrific, very simple, right? Except that all this other junk happens. Well, all you have to do, I think the next slide, now let's skip that one, is put a tank circuit on here, okay? It's a tank circuit. We looked at this in chapter 2, right? You also looked at it in your AC circuits class. This is a resonant circuit. It's a bandpass filter. Works great, very simple. And all you end up with is this spectrum. Carrier, upper sideband, lower sideband. Yay, so that fixed that, right? And this works. I mean, this is actually a practical circuit. Now this over here, you can't really put two signal generators, so to speak, in series with one another. You use a summing circuit here, which you can use an op-amp for that, or perhaps some resistor summing in front of a transistor circuit or something like that. So this is sort of semi-practical, semi-block diagram-ish diagram. Okay, for amplitude modulators on the out, so right here we have a real low level signal, right? This is just wimpy. You can't really put this on an antenna and have it go anywhere. So we have to basically connect it up to a transmitter. And so when we talk about amplitude modulators on the next couple slides, really what we're talking about is the transmitters. And we can either do the modulation and the power increase at a low level where the modulation happens, or we can do it at the output, where at the antenna essentially, where you're basically amplifying the full modulated signal. So that the difference between those two is the low-level modulator and a high-level modulator. So high-level modulators will produce AM at high power in a final amplifier stage, whereas a low-level, it's basically you're amplifying that low-level signal, and then the output transmitter is at a constant power. So let's look at some examples of that. Yeah, so a low-level example of a low-level AM would be a diode modulation, which is just a mixing network, which is what I just talked about, sort of a summing circuit. Well, it is a summing circuit. A little diode rectifier, which gives you your square law function, right, and an LC tuned circuit. So that's just what we looked at. That's the summing circuit, the diode, and the tank circuit, okay? Now the carrier is applied to one resistor and modulating to the other resistor. That's the summing circuit, all right? So they're mixed. Diode does the square law function, which is essentially a rectification, and then the coil and capacitor. They repeatedly exchange energy. That's what the concept of a tank circuit is. And we filter out all the intermodulation products. So here it is. Here's our summing circuit right here. And there's a diode and there's a tank circuit. And this is a little more practical in concept than the last diagram, where you had the two signal generators in series. That wouldn't work. This would work, okay? I would put a little buffer in here probably, maybe an op-amp of some sort, but still, it's good. We can use a transistor instead of a diode. Remember we said transistors, FETs, and BJTs both create a square law function, so you could use this. And this is good because it creates a little amplification too, right? We have basically a common emitter transistor, which we talked about in our semiconductor class, which you had before this, and then the tank circuit is up here, okay? Now this transistor is operated pretty much at cutoff, okay, and the modulating signal will, and the carrier will kick it on, and the tank circuit here will restore the sine wave, basically filter out all of the intermodulation products. There's another semiconductor device you can use called a pin diode. And the way I like to think of a pin diode is sort of like a voltage-controlled resistor. Okay, as it says here, when they're forward biased, they operate as variable resistors, variable based on their bias voltage. Okay, and when you think about it, it's sort of like a voltage-controlled volume control. All right, you know, because a volume control, if you will, is a variable resistor. It's a potentiometer, right? Well, if you could take the knob of the volume control and control it with a voltage, what are you doing? You're basically modulating something, right, with a voltage. Well, that's the whole idea of AM, right? So I look at a pin diode as like a volume knob that is controlled with a voltage. And you got to hook them up like this, okay? So you have these there's two pin diodes here, and there's another way of doing it here. But basically your modulating signal is changing the bias on these diodes, which is in turn amplifying or attenuating the carrier oscillator. It's mostly attenuating, obviously. But notice how the modulating signal is changing the bias on these diodes, okay? And as a result, it changes their resistance. So it forms a big resistor divider, if you will, in series with the carrier oscillator. So therefore, it changes the voltage divider equation, and therefore the output of the whole AM modulator. And this is another way of doing it is all. Pin diodes are used at very high frequencies, by the way, above 100 megahertz. So they're kind of good that way. They've got very small junctions and very low capacitance. Differential amplifier is another way to do it. A differential amplifier, we used a balanced circuit. Let me show you the circuit. This is a standard basic differential amplifier. So you have a plus input and a minus input. It's usually what they say. I don't know, it's V1, V2, but they operate opposite of one another. As one goes up, the other goes down in voltage, and so on. And this is a constant bias or a constant current sink right here, this Q3. Well, what you can do, okay, is take one side of the differential amplifier, ground it, and operate it single-ended, and then modulate the whole thing using that current source. All right, so this is an example of a differential amplifier and using it as an amplitude modulator. You will not have to draw this on an exam or quiz or anything like that. I just would like you to recognize it. The importance of understanding differential amplifiers is also very important because they're used not only in this application, but all different kinds of things. And we talk about those in integrated circuits as well, that class. And then, of course, the output is always filtered. You still have to have your tank circuit, right, to filter out all those intermodulation products. Okay, high-level AM, this is where it gets real hot, right? Stuff can get really hot. So all the modulation is done basically at the transmitter stage. Now, a collector modulator, as the name implies, is the collector of a transistor, which is connected to essentially the tank circuit and the antenna. And we have a transformer involved here, which forms part of the tank circuit. And I always like to show the schematic here. Easy to see. Here's our carrier input. Here's the high power audio amplifier modulating signal with a modulation transformer. So here's your series circuit here, if you will. And it's a collector modulator because we have the carrier input operating this transistor, okay, which is if you don't have any modulation, you have a steady sine wave current going through these two transformers, all right? And look at that, there's a capacitor across the primary of this transformer. That's the tank circuit, all right? That's the filtering happens. The secondary is connected to your antenna and ground. And this works really well. The problem is it's somewhat inefficient because of this high power audio amplifier has to be about half of what your full power. So for example, if you have a 50,000 watt station, you're talking 20,000 watt amplifier. That's moving some air, right? If it was hooked up to a speaker, it isn't. It's hooked up to this primary, this transformer. So this is not usually used in real high power applications, okay? Now, there is an example in the textbook which you should do in preparation for future questions or maybe an exam, which has you calculate the power of this audio amplifier and the current and power going through, actually not the current, but the power going out the antenna and in this circuit based on the various efficiencies involved and so on. And we might look at that in class sometime. Okay, now here's another one, very similar, the series modulator, very similar to what we just talked about, the collector modulator. The good news is that it uses less transformers, I think here. Let's see, yeah. Only one transformer instead of two. It's got two transistors in series, right? And so this one transistor takes the place of the other transformer, essentially. This guy is actually operating very efficiently, Q1, because it's a Class C amplifier, so it's operated at cutoff. It only kicks on when the carrier is at its peak, Class C amplifier. The emitter follower, however, is operating in a very Class A type operation where it's on all the time in one way or in some form or another. So it gets kind of hot, okay? So it's very inefficient. Pretty clean, I mean, in terms of distortion and things like that. That's the good thing about it. One more thing about this Class C amplifier, it only conducts at the peaks of the carrier waveform. So you get this really funky looking signal coming out here, right? That's okay because this tank circuit filters out all the harmonics and all you get is the fundamental. So of the carrier and of course its sidebands. So this takes care of that. So this allows you to operate this Q1 here at cutoff and really just snap it on just really quickly. Transistor that's fully on dissipates no power, theoretically. This transistor that's fully off dissipates no power, right? Fully off, there's no current going through it, so that's no power. Fully on, there's no voltage across it. So that, again, is no power being dissipated in the device. And that's the whole spirit behind Class C amplifiers. They're either fully on or fully off. And that's how this one's operating. Okay, let's look at some demodulators. So they take the modulated signal and recover the original modulating information. That's our lab we did, right? So here's a diode detector. Diode detector is also known as an envelope detector, also known as a crystal radio. Some of you maybe have heard of crystal radios. Notice there's no batteries on this. This can actually work. This will work. You can build this and you can listen to stations, AM stations if you want to. But your AM signal comes in here. We have a little filtering. This is where you would tune it. So these capacitors here, one or both, might be variable capacitors, so you could change the station. Basically tunes in your carrier waveform. There's your diode demodulator, all right? This picks up the envelope of the AM waveform, and then over here we have some filtering, all right? So this ends up with the original modulating signal. We built this in our lab, this exact circuit without the transformer. We didn't need that, but this is what we did in our lab, remember? And it worked, sort of. So yeah, diode detector, positive alterations. It basically does a rectification and picks up the peak value of the pulses, right, of the input. The capacitor is used as a filter, and the time constant of the capacitor, it's all talking about filtering here, is long compared to the period of carrier, so therefore only, theoretically, only the modulation gets through. And as we looked in our lab, we experimented with different capacitors, and the lower the capacitance, caused a lot more carrier bleed through, right? The signal, the demodulated signal was fuzzier, and that was carrier bleed through. We beefed up the capacitance, and that resulted in a better looking demodulated signal, although some of the high frequency components of the modulated waveform were attenuated by that capacitor as well. So kind of got to get a happy medium. And as I said, it's often referred to as an envelope detector. Okay, we can also do synchronous detection, and this is where it gets a little more complicated, a lot more circuitry, not just diodes and coils and things like that. A synchronous detector uses a clock generator or an oscillator in the receiver that's running at the carrier frequency to switch on and off FETs that basically produce rectification, similar to a diode detector. It's much more accurate. It's also called a coherent detector, but they're very accurate and have less distortion. The tricky part is, see if there's a, yeah, it has to make sure, you have to make sure that the input or the carrier, or I'm sorry, the synchronous signal that is being used to switch on and off the carrier coming in, the received carrier, is in phase with that incoming carrier. And you do that with a circuit called a phase lock loop, which we build one of those later on in this course. So here's a schematic of it. Here's the clock, and it basically switches on and off one side or the other of these diodes, which, if this is in sync, 100% synchronization with the carrier, all you end up with is the modulated signal out here with a little filtering. The tricky part is getting this clock in sync with the carrier. So what happens is we pull in the AM signal, we filter it just to get the carrier, feed it into this clock circuit down here. This clock circuit is essentially a phase lock loop. It locks to that and creates this synchronous detector signal. That's something that's left out of this block diagram. Sort of this behind the scenes thing that's going on here. We'll talk about that a little bit more when we do our phase lock loop. Okay, anytime you hear something about balanced modulators, it's basically a lattice or bridge arrangement, we'll see a schematic in a moment, of diodes. And they are used to create a DSP or a double sideband signal, okay? And if you want to generate, we're going back to modulation now, if you want to generate a single sideband signal or a double sideband signal, you use a balanced modulator. So if you want to generate a single sideband signal, what do you can do? Just use a balanced modulator, generate the double sideband, and this filter out one of the sidebands. Now you've got a single sideband. All right, so there's some chips here, 1496, 1596 ICs. You can use some multipliers. Lattice modulator is the same basic concept. It uses a diode ring and a transformer. We'll look at some schematics in a moment. So here's a lattice modulator. You will not have to draw these, don't worry, because they're kind of complicated and wiry to draw. But there's a couple of different kinds, a couple of different configurations. This is a ring style, this is more of a bridge style. So you have a modulated, but the thing you need to remember, okay, is you get the modulating signal coming in here, you have a carrier oscillator here, and the output is a double sideband signal. So what kind of signal does a balanced modulator produce? A double sideband output, right? It's important to remember. And again, the lattice modulator, that's what we were just looking at. They act as switches, basically, and turn on and off, obviously. And the carrier basically turns on and off the diodes with its sine wave. And we can use some chips, 1496. You can look up these on DigiKey. I think they still are available. They don't go really high frequencies, go up to 100 megahertz, so something that beyond that, you have to use the lattice modulators. with low capacitance diodes. Carrier suppression of 50 to 65 dB is pretty good. You can do more with filtering after that. You can also use an analog multiplier, all right, to generate DSP signals. Analog multipliers are much slower, so we're talking about much lower frequencies here. And obviously the carry's got to be a true sine wave. Yeah, the circuit we're using, the 2206 circuit chip that we use in the lab, doesn't really generate a true sine wave, right? It's more like a triangle or trapezoidal kind of wave. And so that's why when we looked at it on the spectrum analyzer, it had all those harmonics. If it was a pure sine wave, you wouldn't see any harmonics. You would just see the fundamental. Okay. And to generate SSB, go ahead, use a lattice modulator and filter out the either lower sideband or upper sideband. Okay. That's what this slide says here. Got to select either the upper sideband or the lower sideband. And so here's a little block diagram. Got your balanced modulator, got your carrier coming in here to the balanced modulator and the modulation. So this box here is the slide 2 slides ago of that diagram. Out comes the DSP signal, right? That's what a balanced modulator produces. There's a sideband filter. You're going to either select one sideband or the other. So that's what this filter diagram shows here. Comes out with an SSB signal, and then we have a linear power amplifier. So all that comes out of here is a single sideband signal, just one lump. We're almost done here. You can also use phasing. This is really, really involved. You actually use 2 balanced modulators, and that eliminates the carrier. But again, you have to use a phase lock loop somewhere. Let me see if I've got a diagram here. Okay, so here's the carrier oscillator. There's a phase shifter, which you can use a phase lock loop for that. 2 balanced modulators. So this is a very complicated circuit. I don't know that there's any advantage to doing it this way versus doing it just using a lattice modulator and filtering. I honestly don't. So you have a modulator. This is the modulation sine wave, right? That gets fed into this balanced modulator, and then the 90-degree version of it into this modulator. So it's sort of an in-phase and quadrature. We call it IQ modulation. Okay, so when you see this kind of thing, or somebody talks about IQ modulation, and in fact IQ demodulation works the same way, but IQ in phase and quadrature, that's what this is. You're basically using 2 balanced modulators with phase shifting to generate an SSB output. Remember we talked about receiving SSB signals and DSP signals. It's kind of tricky because the receiver wants it all. It wants the carrier, it wants the upper sideband, and it wants the lower sideband. And if all it's getting into its antenna is one sideband or the other, or even both, without the carrier, it's not going to be happy. You're not going to be able to recover that in a traditional way using just a diode detector, for example. It won't work because the math gets all goofed up. So what you have to do, you have to recreate the carrier in the receiver. So sometimes we'll have a DSP signal with a suppressed carrier, and that suppressed carrier, it saves power at the transmitter, right? Because you don't have to transmit that big carrier. But the receiver does get a little bit of it, enough of it to lock onto it using a phase lock loop, amplify it, and then everything gets put back together in the receiver. So here's some SSB circuits again. This is basically what we were just looking at. We have a balanced modulator, and that generates everything. Okay, and then we have a low pass filter to get the 3 kilohertz modulating signal. We have an SSB signal coming in here and a low pass filter to recover the intelligence signal. So we can use as a product detector to demodulate an SSB signal that way. Okay, I guess that's my last slide. Okay, this was a lot of very involved stuff. I want you to focus on a few things, particularly the the fact that a balanced modulator generates an SSB signal, single sideband signal, and right here, okay, and you can use filtering to just choose one sideband or the other. So you can put this filter over here or over here. That's important. I would also like you to make sure you understand the process of demodulating an AM signal using a diode detector. That's important because that's what we did in our lab, okay? And the concept of a square law function, where you can use a diode, or at the beginning of this presentation, a diode or a transistor which has a square law function to do the multiplication and the mathematics that are required to combine the carrier and the modulation signal to create a full modulated sine wave. Okay, we'll talk more in class. So good luck, everybody. Thank you.